So. It's not plus high over the walls, but.
She's the cutest thing of my ball. I guess. So small. That's so
I know, good. Hey, especially like a little bit more work if I don't do that. It always does it, because it's just writing is what they had. One from rough draft, one from the application.
That's big.
That's stupid.
I'm so not excited today. I'm not gonna look at my girls.
Yeah, I think. Like you brown and motion. Okay, but say less.
Didn't even try.
Say less.
I always. Yeah, I'm the Wizards supplier, that's my.
You know,
One of those years old.
then it comes to 7,000, you know. Like I saw it like the first round, so tell how many shows I counted just for it to see, right? Yeah, 7,169. No, like my left eye was like, you know what? I was over. That's not bad, and
Okay. Hope everyone's doing well. So let's see. Yeah, thank you for the assignment number 4. Just a reminder that assignment 5 is available and we've covered everything that you need to do it. And then also by the end of today, please sign up for the last of the Phys 232 experiments, experiment number 5. Okay, so the things that we've been working on is trying to find out how to determine the best intercept and slope of a straight line that goes through a linear set of data. And so we calculated this. So if you measure xi and yi plus or minus sigma I, then we know everything in here and we can just calculate exactly what the best intercept and slope are. That little parameter delta is also determined by the measurements. We also then applied propagation of errors to these two expressions, and we determined the uncertainties in the intercept and slope. And one of the nice things about those uncertainties is that they are determined from the same quantities that we would have to calculate in order to find the slope and intercept in the first place. So for example, this delta, we need it to get A and B, and then these two sums appear, well, in fact, they appear in the sums to calculate delta. Okay, so once you found A and B, it's actually not extra work to find the uncertainty because you already have that information. We also showed that these uncertainties are exactly the diagonal elements of this covariance matrix, we called it. It was when we wrote down our system of equations as a matrix, we called it A. And then we ended up taking the inverse of that. That A inverse is the covariance matrix. And these are exactly the diagonal elements of that covariance matrix. So today, I just want to go through, today's actually pretty simple, pretty straightforward stuff. I just want to go through some examples of why linear fits are so important and so common. The reason that linear fits are useful is because there's no guesswork in determining the slope and intercept. Like once we have our set of data, we just calculate exactly what the best values are. There's nothing, there's no approximations, no estimates, anything like that. So I just want to go through some examples of how we can make use of these linear fits. Of course, you use them all the time already, but I just want to emphasize this fact. So let's suppose that we have a set of data where we've measured y as a function of x, and then we have some error bars on our data points. Maybe it looks something like that. And then we're going to try to put a straight line through our data, and maybe our straight line looks something like that. And the equation of that straight line is y is equal to an intercept plus a slope times x. And the intercept would be right here where x equals 0. And so this would be the value of b. And then, of course, the slope, the way we've written it, the intercept is a. Better get that right. So here's a. And then the slope b would be determined by the rise over the run, something like that. Okay, so we now know that we can determine best fit values for a plus or minus sigma a and b plus or minus sigma b based on our measurements of xi and yi plus or minus sigma I for I is equal 1 to n. Okay. So sometimes it's obvious how we could take a set of data and perform a linear fit. Sometimes it's not so obvious, but when it's possible, we should try to manipulate our data so that we can plot it as a straight line. And the reason, the motivation for doing that is that if we can linearize our data, we can always apply these best fit algorithms that we've developed easily and without any guesswork. We'll see a little bit later in the course, I mean, maybe in a couple of weeks, that when you have functions that are nonlinear, they have like some complicated shape, then there is going to be some guesswork involved in trying to find the best fit parameters. So to avoid that, we should use our linear fits when it's possible, okay? Internet connection is not stable. Well, suck it up. Okay, so this is easy to use when we have an obvious linear dependence. And so it's easy to come up with examples of that. So let's imagine that we have an object in free fall. So we have some mass m, and the force on that is m times the gravitational acceleration. And we could write down its speed is v is equal to v naught plus, well, I guess we should do minus g times t if we're taking positive to be upwards. So here is the speed as a function of the time, and we can see this is already in the form of a straight line. So we're going to measure v plus or minus sigma v as a function of time. And if we compare this to our equation of a straight line, so let's, here, I'll put this as b times x. Then we can make these obvious identifications. If we plot on our y-axis the speed and on the x-axis the time, then we'll get an intercept that's equal to v naught, the initial speed, and we'll get a slope that's equal to minus g, the gravitational acceleration. So maybe we're doing this experiment maybe to try to determine the value of g, and so we'll get that from the slope. Okay, so if we set, we're going to set y equals to v and x equals to t. And if we do that, the intercept is equal to v naught and the slope is equal to minus g. So then when we make that plot, we would have, actually, let's put my x-axis over here. So here's my time axis and here's the speed. Maybe the ball that we threw had an initial speed up. And so initially its velocity is positive. And then it starts to slow down as it falls. And then eventually the speed comes zero, changes direction, and becomes negative. And so we get some data set like this, and we put a straight line through there. Well, I don't love that straight line, but that'll have to do. And so this intercept when t equals 0 would be the initial speed v naught. Okay, so that's a case where it's, you know, probably you would look at v equals v naught minus gt, and you very quickly identify that as a straight line, and you do a linear fit, no problem. Okay, so sometimes a pair of variables may not be strictly linearly related, but often we can still use a linear fit to interpret the data. Okay, and so we'll do another example. It'll be another free fall example. So objects in free fall and so let's assume that this time it starts from rest. Okay, so we're going to take some object, it starts from rest, and we're just going to release it. In this case, we're going to measure not the speed of the object, but its displacement. How far has it moved? So one of our other kinematic equations is d, or x equals x naught plus v0t minus 1/2 gt squared. If we're starting from rest, the v0t is not there, and so we just end up with 1/2 gt squared. Okay, and so this is not, you know, d is not linearly related to the time. It's a quadratic thing, right? So if we were to actually plot this, it would look something like this. And so maybe we measure some data points and they, I don't know, they sit something like this. So again, it could, if we drop this fall from like a hilltop or something, it starts with a positive position where maybe the ground is, sorry, maybe we drop it from a cliff. And so we'll say the ground of the cliff is a position of 0. So we start with a positive position, release it, it'll fall down past the ground and have some negative position. And the change in position gets greater and greater for equal time intervals as the little mass accelerates due to gravity. And so here it would be d, this is the intercept, would be d0. Okay. So instead of doing something like this, how could I analyze this data with a linear fit? What would I want to plot? If I wanted to graph this in a way that I'm going to get a straight line, what would I plot on my y and x axis?
Take a lot of each side to get.
Yeah, that's not going to help us in this case because it might help us if we didn't have the d0 here, but I can't do anything with a ln of a plus b, right? Again, if I take the square root, because of the d0, I'm not going to end up with a Like I'm not gonna take the square root and end up with a t.
Could you not just call D 0 though, and then you
Yeah, I could, no, but if I didn't want
Could you make the y-axis d minus d naught?
Yeah, you could do that. Then what would I have to put on the x-axis then? T squared, right? That's the ticket. I don't need to do d minus d naught. I just need to make my x-axis t squared. And so I'll say x is equal to t squared. So instead, we can linearize. And so today's topic is all about trying to linearize data so that we can plot it in a way that we're going to get a straight line and then perform a linear fit. So we can linearize the data by plotting y equals d versus x equals t squared. Okay, so then if we did that, so we do, here, I'll just rewrite our original expression. And below it, I'll write our equation of a straight line. And so what we're going to do is we're going to identify t squared as x and the position d as y. And then it's clear that the intercept will be d0, the initial position, and the slope will be 1/2 of g with a minus sign, so minus g over 2. Okay, so in this case, a plot of d versus t squared as intercept a is equal to d0, the initial position, and slope b is equal to minus g over 2. Okay, and so if I was to plot that data as a function of t squared instead of t, then it will be a straight line. This will be the intercept, the initial position, and then we'll get our data points. That'll look something like this. Still, we can have our position go through, go from positive to negative, go through d equals 0. And so maybe our straight line looks something like that. Okay, good. All right. So let's do an example from the lab. So another example. Okay. In the thermal waves experiment, in thermal waves, the amplitude of the fundamental Fourier component is A1, I think following the notation in the manual, was equal to 4T0 over pi times the exponential of minus the square root of omega 2 alpha times x. Let me just remind you, for those of you who have done thermal waves and those who didn't do it, in thermal waves, you have a heater at one end of a long copper bar, and you're turning the power to that heater off and on at some frequency f. So omega is just 2 pi times f, whatever frequency you choose. And so you have a bunch of thermometers at different positions along this copper bar, and the thermometer positions are a distance x away from the heater. So that's what x is, how far away you are from the heater. T0 is just the temperature at the heater when you turn the heater off and on. It's going to have some average temperature at the position of the heater, and so that's related to T0. Okay, so that's what all those things mean. You're going to measure the temperature at one of the thermometers, and you'll see some kind of oscillation. And you'll do a Fourier type analysis to figure out the amplitude of the oscillation at the frequency that we can either off and on. And that's what A1 is. So A1 is something you can measure. Anyway, so that's what all these things mean. So what I'm going to do is I'm going to measure A1 as a function of X. What should I do to linearize these data? This is the time to say it. Yeah, right. We're going to take the ln of this. So to linearize, we're going to take the ln of both sides. And so we'd get the ln of A1 is going to be equal to, okay, so we're going to have the ln of a product. And so I'll assume that what I'll do is I'll take the 4T0 over pi as one of the products, and then the exponential as the second one. And so we'll end up with the ln of 4T0 over pi. And then it would be plus the ln of the exponential, but of course the ln and the exponential cancel each other out. So we'd end up with a minus square root of omega over 2 alpha times x. Actually, I guess I didn't tell you what alpha is. Alpha is called the thermal diffusivity of the copper bar. It's the ratio of the thermal conductivity and the heat capacity. Okay, so it's a material property of the copper. And that's what we're trying to measure in this experiment. Okay, so then that's fair enough. So if we say y is equal to a plus bx, then we can identify as y the ln of this amplitude, and x is just x, the position of the thermometer. So we have a bunch of thermometers. We do this measurement for a bunch of different values of x, and we get a bunch of different values for this amplitude. So we're going to plot the ln of A1 versus x, and we're going to get an intercept. Let's see, A is going to be the ln of 4T0 over pi. And we're going to get a slope of B is equal to minus square root of omega divided by 2 alpha. Okay. All right. I mean, I guess we could draw it. So this would be x, and this would be the ln of A1. And we'll just have some data points in here. And I mean, this just looks like all the other linear fits that we've sketched out. It'd be something like that. Okay, so once you've done this and you've found the slope and its uncertainty, you can use it to find alpha. So in the thermal waves experiment, we use the slope B to find the thermal diffusivity alpha of copper. Okay, so B is equal to minus the square root of omega over 2 alpha. So we could square both sides, and we could say B squared is going to be equal to omega over 2 alpha, or solving for alpha, it would be, let's see, omega over 2B squared. All right. Now let's just do a bit of practice of propagation of errors, because what we would want to do is also estimate the uncertainty in alpha. And so the uncertainty in alpha squared, let's say, is going to be by propagation of errors, d alpha dB times sigma b all squared. And, you know, I guess in principle, we could have an uncertainty with our frequency, d alpha d omega times sigma omega squared. In practice, the uncertainty and the frequency is set. I mean, the frequency is set by a function generator, and we could set the frequency very accurately. So this is going to be very small compared to the uncertainty probably in the slope. And so in practice, we would probably ignore this term. But let's just, for the sake of completeness, we can include it. Okay, so d alpha db. So we have a b to the -2. So we'll get a -2 omega over 2b cubed sigma b, I think, squared. The minus sign is not going to matter. And then the derivative with respect to omega is just 1 over 2b squared. And then we'd have sigma omega squared. And so therefore, the uncertainty in alpha is equal to the square root of, let's see, the 2's cancel. I don't care about the minus sign. So we get omega sigma b over b cubed squared plus sigma omega over 2b squared, all squared. Okay, so you would get sigma b from your analysis of the linear fit, and sigma omega you would have to estimate from maybe the specs of the function generator or something like that. All right, good. Let's see, did I get that right? Oh, I think so. All right, so let's do another example, one that's maybe less obvious. So how are we doing time-wise? Oh, good. We're rocking. So another example. This example is actually something that it's a technique that's used in current research. All right, so if you were to measure the thermal conductivity of a metal at low temperature, what you would find is that it has two contributions. You have thermal conductivity of the electrons that are the conduction electrons that are flowing inside the conductor. But then you also have in metals or any material, you have a lattice of atoms, and that lattice can vibrate. And so those vibrations can also be used to transfer heat along a material. So you would learn about this if you were to take, we have a solid state physics course, 474, typically taught by Hopkinson. So anyways, that's something you could take in the future if you wanted to. So the low temperature thermal conductivity of a conductor is typically of the form. So thermal conductivity is usually denoted kappa. So that's Greek letter kappa. And then it's some coefficient times T plus some other coefficient times T cubed. And so this linear term is the electron contribution. And this T cubed term is the lattice, or sometimes called the phonon contribution. Okay, now what we're going to do is we're going to imagine that we measure kappa as a function of the temperature of our material. Now that's clearly nonlinear, right? We have a linear term and then we have a cubic term. And so if you were to plot that, it would not look like a straight line. So this does not appear to be easily linearized. Let's say at first glance. Can anyone think of something we can do, some simple manipulation that we could do here to make this look like a linear function? So I'll give you a hint. On our y-axis, we're not going to plot just kappa. So in all our other examples, we had like, well, A1, we ended up plotting the ln of A1. Here, D was equal to some stuff, and we plotted D on the y-axis. V was equal to some stuff, we plotted V. Yeah.
You do kappa minus one of the terms?
Yeah, you could, but let's suppose that we don't know either the C1 or the C3 coefficient. So if we subtracted one of those terms, we wouldn't know what to subtract because we don't know those coefficients. I think you're on to something. I don't want to do times. Yeah, let's try kappa divided by T. Let's try kappa divided by T. So kappa divided by T is going to be equal to C1 plus C3 T squared. And so now we have a term that doesn't have any temperature dependence. And so this would be like an intercept, a constant intercept. And then we have a term that does involve T, and it's a T squared in this case. So what should we plot in this case? Yeah, good. So we plot kappa over T versus T squared. If this is y is equal to a plus bx, then we're going to take T squared for our x, and we're going to take kappa over T for our y. And this will have a intercept of the C1 coefficient. So A is equal to C1, and it would have a slope of B is equal to just C3. So in fact, that's very easy. As soon as we do our fit, we don't have to do anything else. The intercept and its uncertainty gives the first coefficient and its uncertainty. The slope and its uncertainty gives us all the information about the second coefficient, C3. Okay, and like I said, this is used all the time in current research. So we plot T squared over here, kappa over T over here, and we would end up getting some data points that, I don't know, look something like this, I guess. And we put a red line through here. That's our data. Over here is our intercept, and this is going to be C1. Okay, good. All right. I've got a couple more examples here. So another example. This one is going to, again, be from the 232 lab, one of the experiments we do. So sometimes a pair of variables cannot be, cannot be strictly linearized. And so in the black body radiation experiments, we have an expression for the intensity of the emitted light, and so as a function of the temperature of the furnace that we're heating up. So we heat up a furnace, it glows some kind of red orange color. We measure the intensity of that glow as we change the temperature of the furnace. So the intensity is a bunch of constants times this thing, 1 over e to the hc over kb t lambda minus 1. And so obviously we're going to measure I lambda versus t, which is not linear. Okay. In this case, we see an exponential there on the right-hand side. And so the instinct is to try to take the ln of both sides. And that's a good idea. But the issue is that the -1 prevents us from making any progress with that ln, because the ln of an exponential plus or minus another term, I can't do anything with that. Okay, so I mean, if you've done the black body radiation experiment, you know that we analyze it with a linear fit. And in this case, what we have to do is we have to make an approximation. So, however, under certain conditions, we can make valid approximations that allow for the data to be linearized. Okay, so in this case, the approximation we want to make is we want to get rid of the -1. So in this case, if hc over kBt lambda is much bigger than 1, then we can approximate e to the hc over kBt lambda minus 1 as e to the hc over lambda kBt. Okay, so we just got rid of the -1. For some reason, I switched the order of my variables, but I guess that doesn't matter. Okay, so if you're going to do something like this, all you have to do is make sure that this combination of values is always much bigger than 1. HC and KB are all constant, so there's nothing to worry about there. Those are just numbers. But you have to consider your full range of temperatures and your full range of wavelengths, and just make sure that any combination of those values always satisfies this condition. Otherwise, you'll break the approximation, and when you try to plot your data, even though you think you've linearized it, it'll still look funny. It won't look like a straight line. In fact, I guess part of what we do is when the temperature, never mind, I don't want to say that because I'm going to say something dumb. Okay, so forget it. You just have to make sure that that approximation is always valid. Okay, so if you can do that, then you end up with this intensity is approximately 2c squared h over lambda to the 5th. And then we have that 1 over the exponential -1. But we're going to get rid of the -1. And that just allows us to write the exponential in the numerator as long as we put a negative sign in front of the argument. Okay, and so now it's still not linear, but now we can take the ln of both sides and make some progress. Now, makes sense to take the ln of both sides. So we'd have the ln of the intensity is approximately equal to the ln of all of those constants. And then we would end up with minus HC over lambda KB, and then I'll write it as 1 over T, like so. And so if you compare that to Y is equal to an intercept plus a slope times X, we'll take the ln of the intensity for Y, and we'll take 1 over T for X, so that a plot of ln intensity versus 1 over T has intercept. Let's see, A is going to be, well, A is some complicated thing. And then B is equal to minus HC over lambda KB. And so the way we do the experiment is we say, all right, we are going to assume that we know C and KB, and then when we set up the logger pro staff, we select the wavelength, so we know the value of lambda, and so we can use this H. Yeah.
When you make an approximation like that,
Yeah.
how do you know where to draw the line?
Oh yeah, so all you have to do is we would say, okay, we know that our temperatures are going to be something like room temperature up to about 1,000 Kelvin. And we know that we're going to use a spectrometer that is operating in the visible light range. And so I know that my wavelengths are going to be something like 400 to 900 nanometers. And so what you would do is you would choose the combination of values that's most likely to break the approximation. So what I would do is I want this to be, if I want to break the approximation, I want that to be small. Okay, so in order to make this small, I would choose my largest values of temperature and lambda. So I would say, okay, my maximum temperature is about maybe 1100 Kelvin. My maximum wavelength is 900 nanometers. And I put those numbers in and see if that, if this condition is satisfied.
But how do you define much larger than 1? Like,
oh, 3? Yeah, it's typically like maybe a factor of 10 or something like that. Yeah. So there's no golden rule for that. But what you would do is, I guess practically speaking, all you would do is if you think you could make an approximation like that, you would do it, then plot the data. And if it doesn't look linear, then maybe you suspect that something's gone wrong. Yeah. Right. Okay, good. So then what we could say is we could find H using minus lambda KB times B over C. You might notice here that you could also find H from the intercept, right? Because we know C and we know lambda, and so we could find that from the intercept as well. So in principle, that's true. In practice, when we do the experiment, we're using an uncalibrated spectrometer. So we're measuring relative intensity, not absolute intensity. So that means, if you've done the black body experiment, you know that your intensities go between 0 and 1. And so those aren't in any units. Like an intensity would be what? Like probably an energy per unit time per unit area. So joules per second per meter squared or watts per meter squared. What our spectrometer does is it says, I don't know the actual value of the intensity. I just know that I can determine when, say, the intensity doubles. So I know that an intensity on my scale of 0.2 is twice the intensity of 0.1, but I can't tell you in actual real units what the value is. And that's what stops us from using the intercept to find the Planck's constant. Okay, good. All right. So that's a bunch of examples where we can linearize data. Sometimes it's just not possible. Okay, so sometimes it's just not possible to linearize a data set. Okay, so for an example, let's think back to our favorite course, Physics 231, LRC circuits. So we did a lab where we had a function generator, which was providing some input voltage, let's say V naught. And then we had an inductor and a capacitor and a resistor all in series. So this is supposed to be an inductor. Maybe I could draw a better inductor. So inductor. Okay, and then here's C and here's R. And what we're going to do is we're going to measure the voltage across the resistor. So in fact, what we actually did is we measured just the amplitude of the voltage. So we're going to measure the amplitude of the resistor voltage divided by the amplitude of the output of a function generator versus omega. Omega is just the frequency, 2 pi times f. Okay, I'm not going to derive it, but we had this result for this ratio. And it looked like the following. One way to write it was 1 plus omega L over R minus 1 over omega RC squared. And let's just suppose that for some reason, we didn't know L and R and C. And so what we're going to do is we're going to try to make these measurements to find these values. Okay. There's not really anything we can do to linearize this, right? I could square everything. I could get rid of the square roots. But then I still have 1 over 1 plus something complicated. I could square everything and then take the inverse. So I would have V naught over VR squared is equal to 1 plus this stuff. I could even subtract off the 1 and then take the square root, and then I have omega L over R minus 1 over omega RC. But then I still have a linear omega and a minus 1 over omega. Like it's hard to see exactly how you could linearize this data. So in fact, if you were to plot this, you'd have omega and you'd have VR over V naught, just amplitude ratio, and that looks something like this. So it looks something like this, and here's our resonance frequency, and this peaks at a value of 1. So, okay. Oh, why aren't you moving? Oh no, I'm stuck. Let's see if I close it and open it. Does that help? Nope. Oh, okay. I can't scroll. Okay, what I'm going to do, just close it completely. And let's bring it back up. Oh, you little piece of... Okay, all right, we're back again. Let's try. There we go. That's what I wanted to do. All right, so this last example is just to motivate the fact that linear fits, although they are by far the most common type of fit and the easiest to do, it's not the be all and end all of data analysis. So sometimes we need to develop and implement new fitting methods. So we need different fitting techniques to extract the desired parameters from non-linear data sets. And that's what we'll start to do on Friday. So in fact, we're gonna end up doing two additional types of fits. One will be fits to data that follow a form of like a times a function of x plus b times another function of x. Nice of you to join us. Plus c times another function of x, where if we want to find a, b, and c, we'll develop that method, and we'll find that just like for the linear fits, we can exactly determine the values of the parameters, those coefficients a, b, and c. And then they'll have a third class of functions where we have these nonlinear functions, and we'll have to develop another technique to handle those ones. That last technique will require some guesswork on our part. Okay, so that's it. Thanks very much. We'll see some of you in the lab. All right.